So you're all welcome back, and what we're going to be looking at now in this second lecture tonight is on feature detection, which was actually the title slide was feature, but obviously edges are the simplest of features, which we're going to build upon now. So intuitively, computer vision is about seeing things in images, so trying to find things in images. We tend to step up from the word things though, and we use more expressive terms like features. So we're going to look for features. Now, the thing about features is they should be describable. Now, I don't necessarily mean that they should be describable in English words or that. I just simply mean that there should be some mechanism whereby digitally we can describe them, and so that we can describe them in such a way that they can be told apart from other parts of the image. Okay, so in other words, there can be some uniqueness to them. And this becomes particularly useful when we want to find the same feature in two different images, okay, which is where we're ultimately going to be going with this sort of thing. Okay, so but think about the example. If you're meeting somebody in Dublin, for example, what you normally do is I'll say you'll meet them under the clock at Eason's, or since the spire was built, you might decide to meet them at the spire, but you're not going to say I'll meet you at the footpath. Okay, because nobody knows what footpath and where you would do that. So you need to come up with somewhere that's unique. So it's very much similar in an image. When we're trying to find features in it, we want something that won't be mixed up with any other feature anywhere else within the image. So one of the main reasons for acquiring a good description of a feature is that we want to be able to recognize the same feature in another image taken from another position. Part of the whole point of this course, multiple view geometry, we're going to be seeing things from multiple views. And we want to be able to pick out the same thing in two different images, so that from there we can try and work out something about the world in 3D, despite the fact that we've only got two-dimensional images. Now, the trouble is with seeing things from different views is that they often change shape. They might change in brightness because there might be a time gap between when the two things happened, or simply because of our positioning, we might see more light on it from one position than another. So we need it to be invariant to a lot of different things, but then we need to have certain things that are going to tell us that it's the same feature depending on what angle we see, even with seeing it from some fairly extreme angles. So feature detection and matching is an essential part, is essential to many computer vision applications, and we will be particularly using it. It allows us to stitch images together. So if we've got lots of images and we want to stitch it together in some form of a panorama, for example, then we need to find the same places so that we can stitch them all together and find the right place for them to meet. We will also see later that it helps us determine the position of cameras that took the images. So for example, if we've got two different views and we want to find out where were the cameras positioned, this will turn out to be very useful as well. So in terms of images, features that are easy to localize, and by localize I mean we're able to tell exactly where the feature is, are called key point features or interest points, and usually the patch of pixels surrounding the point location are used to describe them. So we can't normally tell anything from an individual pixel. That's not going to be useful because it's just a brightness value, but it's the combination of a certain number of brightness values beside each other, their relationship to each other, that's important, rather than specifically the brightness. So edges are useful, particularly if the edge has an interesting shape that makes it recognizable apart from other edges. So the orientation of edges is important. For example, what direction it's going to be in. Edges are often formed by the boundaries between objects, so they can be useful for determining one object. If one object, let's say an object is in front of another, okay, so if we take my hands here, you can tell whether my left hand is in front of my right hand, because we can see that there's a boundary there. We can see that one is in front of the other, and you can probably assume that my watch is on my left hand, even if you couldn't figure that out from which way the camera was oriented. Okay, it looks wrong to me because I'm looking at the webcam, but you're seeing it correctly. So we can tell when one thing is in front of another, and just to get you familiar with the terms, if one object blocks another from view, this is called occlusion, or it occludes the other object. We can also group edges together to form a longer sequence in images, and lane markings lane markings in an image. Let's say if we're in a car, we're taking a video of the road in front of us, we can pick up lane markings And if we can pick up lane markings and we can pick up a combination of them, we can tell maybe what direction the lane is going in. And that might be useful to us if we want to keep within the same lane and see that we're not wandering out of it. These can also be useful to find the vanishing point or the line at infinity, which are also useful ideas for figuring out things about where we're positioned in a perspective image. So 2 terms to get to know are sparse and dense, and these mean exactly what you would expect them to mean. Sparse means relatively few with big gaps in between, and dense is many with small or no gap in between. For point correspondence in the first instance, it's acceptable and usually desirable as well to have a sparse set of well-described points in multiple images so that we can determine the maximum from these with the minimum calculation. Now, as well as that, in the particular application that we're interested in, which is of course the automotive sector, we're normally constrained by computational budget, and that means that oftentimes we're going to want to find the most efficient method for calculating whatever it is we want to do. Now, that's not to say there wouldn't be reason for using dense methods, particularly if we want to get an idea. If if we're parking a car and we're driving slowly, we want to get a good picture for maybe the driver of the car as to what things are going to look like. That would be more in terms of dense methods. But if we just want to find out some individual points that we're going to work with within our image, then sparse would do, and sparse will be much more computationally efficient. It's also the method that we would generally use if we're trying to find the motion of the camera. So, for example, if we want to find out the motion of the camera, and of course if the camera is attached to a car, this tells us something about the motion of the car, then we only need sparse techniques in order to have a certain number of points in order to give us that information. So more is not necessarily better, and it may be worse in terms of grabbing these features. If you consider thousands of point correspondences and we want to use these to determine only a few unknown parameters, you've all done in linear algebra, you'll have done, how many unknowns you have and how many equations you need to solve them. If you've got 1,000 equations and all you need is to solve 3 or 4 points, then you've often got a problem, because if there's any noise in those and if any of the points are outliers, they're going to push everything out. Whereas what we really want is just enough of those points, and we want them to be as robust and correct as possible. The more we take, the more likely it is that we're going to be getting these outliers. Now, obviously, if you only take a few points and you get outliers in those few points, you're in big trouble. But the idea would be that we have some mechanism to tell what's a good feature, and we only take the top X number of features in what we want. So we only need enough points to give us enough independent equations in the unknowns to solve the problem. The small number usually means we will pick the best, the most likely to be correct, and get close to a single answer, correct answer for each of our unknown parameters. Key points have the advantage of being able to match even in the presence of occlusions and significant changes in orientation, which is hopefully what we're going to try and find. So there are 2 broad approaches for how we would go about this. The first one is that we find the points of interest. We go for our first image and we find the points, find some interesting points within it. Okay, so we look at it and we say, well, that'll be an interesting point, that won't, and so on. Okay, we normally have some sort of software algorithm for doing this. Then we get a description of those features, and with a description or a small patch of pixels, what we do is we go to our second image and we go searching for each of these in the other image. Now that means searching all over the image, or it means searching in a small neighborhood close to where they were found in the first image, because you might expect, well, we're not expecting much change between the images. Now that depends on what type you have, right? Whether you've had what we call a small baseline or a large baseline, which is, do we expect that there's only been a small change between the 2 views, or do we expect that there's been a large change? If there's been a large change, we're going to have to search all over the place. So it works well for small baseline, that idea, when the distance between the image viewpoints is small, because we've got a descriptor and we're only going to check the small neighborhood around where that position was in the first image. We do that in the second image. So this might, small baseline example might be consecutive frames from a video sequence where only small changes have occurred. In the case of video, this can be used, for example, to steady a shaky video, because a shaky video will move a little bit, but not much. So all we have to do is find the second, find how far it's moved, and that tells us how much of a shake there's been, and we can try and correct for that. In the case of autonomous vehicles, we'd normally be taking at some sort of video frame rate, but if we're moving at 60 miles an hour, you'd have to determine, well, what's the gap between one frame and another? How far have we moved, and therefore how different is the viewpoint going to be? So it depends very much on the speed that the vehicle will be traveling. So our second approach is to find points of interest separately in each of the images. Okay, so go to the first image, find interesting points. Go to the second image, find interesting points. Now you've only got a small set of both. And then what you do is you go and you see if any of these seem to match each other, if they look like each other. So this is useful where the baseline is large, so where you're stitching panoramas or something like that, and you've got a wide gap between the two images. That can be the useful way, because if you don't do that, you're going to be searching for quite some time in order to try and find where you're going. So there's three stages that we will go through in finding the correspondences. First, detect the features that you're interested in. Secondly, describe the features you have found. So you need to come up with some sort of a description. We'll be keeping to fairly simplistic features here, but there are very good methods, things called SIFT, which is scale invariant feature transform. I can't remember what the T stands for. But they would have very very descriptive ways of describing the features to try and tell them to try and tell when we've got the same one in different sort of places, right? What we then do is we try and match the features between two images, or we try and track. So tracking is normally in the small baseline where you're trying to follow where it's going and you're trying to get a sense of how things are moving. So rather than just saying it's in this position in one, it's in this position in the other, over a set of images, we might try and find what is the direction that something is traveling in. Maybe it's what direction is the camera traveling, in which case the environment will change relative to the camera, or it might be that something in the environment is moving and we want to track that. Because if you track that, let's say for example it's a pedestrian and we want to track where that pedestrian is moving, we want to see that they're going to come, whether they're going to cross paths with the moving car, and as such whether we need to be taking some evasive action or not. Okay, so tracking is a very useful one to be able to do. So to match these with matching and tracking would be to match these with features in other images, or to track features in the small baseline. This would be used to check only a small neighborhood around it and then decide where we're moving in. And we'll look at more of that as we get later in the course. So what makes a good feature? Now I already said, if you're meeting somebody in Dublin, you would be saying I'll meet you under the clock at Eason's, or I'll meet you at the Spire. So in an image, how does that translate? What does that mean? So clearly, a clear blue sky or plain walls are very poor, because there's one bit of it looks the same. So they look the same everywhere, and this goes for, in the automotive setting, tarmac, asphalt, pavement. The whole road in front of you all has a tendency to look the same. Now it's not perfectly that way, and there will always be texture there, but whether there's enough for you to be able to say that that's really different from some other part of the road, that's difficult. Okay. Single dots are not particularly good, because one single dot looks the same as a single dot elsewhere, so they're hard to tell apart. What about an edge or a line? Is that good? Well, these are better, but if we are tracking a line and the movement is parallel to the line, then all the points will look similar, and we can only deal with the end point. So if we draw a situation like, let's say I'll draw a line there, okay? And let's say I've picked a point here on this. Does that look any different from... Oh, I've picked up both of them there. I'm not going to be able to separate them. It doesn't really matter. Does that look any different from that one there, is the question. And the thing is, it doesn't. Now, if we happen to be moved, if we moved in this direction, well, it does look different. Or if we just moved that far, we can see that there's a change. So any of it that's going in that direction we are going to see that difference, but any of it's that's moving in this direction, we're not. And so we end up with this situation being where, you know, it'd probably be unusual that we happen to match exactly to be following in that particular direction, but we lose any information that is along this axis. So even if we're moving in this direction here, we can only take the component in that direction and not the one in this one, so we lose all of that. Okay, so it's important to kind of keep that in mind when it comes to these descriptors. So they will not be particularly useful in finding what we're looking for. So this is, so an edge or line, that will, these are better, but if we're tracking a line and the movement is parallel to the line direction, then all points on the line look similar, and we can only deal with the endpoints. The problem with the endpoints is that one endpoint looks the same as another, and if it's moved a significant distance, so if you think about something like lane markings, well, the end of a lane marking, either end of a lane marking, looks the same as the next lane marking. And if you don't have a sense of how fast you're traveling or how fast they're moving through it, are you going to miss those lane markings? Or are you going to attach one descriptor of the end of a lane marking with another descriptor of the end of a lane marking? And of course, you could mix them up from one side of the image to the other side, but you'd hope that your algorithm, you would kind of keep that in mind and say, well, I don't expect the lane marking to move from left to right. Of course, if it's a situation where you're trying to keep somebody in the lane and they make a very sudden movement from one to the other, which they might do if they're overtaking, between frames we do expect quite a lot of lateral movement, and so you'd have to be taking all those things into account and taking account the speed that they're doing in order to try and get an idea of where you expect features to move and where you would go looking for them. That said, for all of that, corners are usually the best. So edges where we have gradients or change in brightness in more than one direction, they're the easiest things to tell apart, that if we see it from some other direction, the directions of the gradients, you know, we might have that, and then we might have it moved over this way. That will have an effect. So, we should still be able to tell them, because if we're able to tell that it's the same angle in both cases, we can get an idea that we're looking at the same feature. So gradients in at least two significant orientations is good, and these are the easiest to pinpoint in terms of our simple features. So when looking for good features, a useful technique is that of autocorrelation. How many people have come across this term, autocorrelation or cross-correlation? Both of those terms. Now, I did mention correlation in a previous lecture, so hopefully you have come across that idea, but have you come across this idea, autocorrelation? Okay, so this seems to be mostly no's. I don't know. Yeah, Maurice, a no as well. So what's the autocorrelation? Now, autocorrelation is the idea where you're actually checking whether an image patch looks the same as some other image patch in the same image. So rather than you cross-correlating it with some other image, you're checking it against its own image. This is the idea of the auto. And more than that, you're normally checking it against areas that are very close by. So what autocorrelation really tells you is that if you do a correlation between one patch of an image and another patch in the same image that's very close by, and it correlates well, in other words, it looks like it, then what that would tell you is that those don't look different. Sorry, what do you mean by echo? What's is that are you getting a bad echo on the microphone? Is that what you're telling me? Oh, sorry. Okay, sorry. On a paved road. Okay, so yeah, or tiled to that. Okay, sorry. I see what you mean. Yeah. Okay. So where you're going to see the same thing. So again, yeah, of course, if you correlate something with, so if you have something like a checkerboard pattern, I think is what Carl is on about here. The idea would be that if you correlate it with something close by and you happen to find that same pattern again, that would correlate well. Okay, and that would be exactly what would make something not be a good feature. So if it looks very similar to some other part of the image, particularly another part of the image that's close by, we now will not be able to tell it apart. So this mightn't just be a checkerboard pattern or something like that. This could be just something that's very plain. So for example, if I test that section there against this section here, those are going to correlate very, very well. They look exactly the same because they're both white. Okay, but if I correlate it against that, and I correlate that, and I check up here, those two things are not going to correlate well. They should be the same shape. I haven't drawn them perfectly the same shape, but they don't look like each other. Okay, so they would be somewhat distinctive. And if I was only checking in a small neighborhood, like that, if I was only checking in a small neighborhood, then the bottom of that G does not really look like anything else within that neighborhood, and therefore that would be a pretty good feature for that. Okay, but clearly any of these things down here and so on, they wouldn't be particularly good. And that O is not particularly good because it looks exactly like the one beside it, so that wouldn't make a very good one either. Okay, so so this is the idea of autocorrelation. What we do is we correlate it with areas that are close by, and if they don't look like it, that's a good thing. And the more they don't look like it, the better, because that means that it's somewhat of a unique feature. Okay, so test a patch of an image against a small region around it. If it correlates well with the positions around it, then it must look like the positions around it, and it is therefore not a useful patch. On the other hand, if it correlates poorly with the surrounding region, it must be very different from them and look unique, at least within a small defined region. So if we've got only small movements occurring, then this can be very, very useful. Okay, so we've got some maths to describe this. The AC stands for autocorrelation, and the E is energy. So we tend to use things from other parts of physics or that. So energy would be, the bigger the number this is, the more they look alike. So we're looking for low values of this as it happens. Now what we do is we define some function to be a window, which we say this is the region within which we are going to look. Okay, now that window could be just a square window, or it could be like a Gaussian, where we say, well, we're going to look within a certain circular region around us, but I'm going to take more importance to the central pixels than I am to the ones around it, and I'm going to do that in some sort of Gaussian form. So that what I'm basically saying here is, I'm going to look for correlations, but if the correlation is very close by, it gets a big number, and if the correlation is much further away, it gets a much smaller number, so that I get a good sense of what's going on. This is a decision we make ourselves. We decide what that window is going to look like. What do? We get the same image in both cases, which we've called I0. So we get the same image in both cases. We pick our pixel values based on the I value here. So we go around to each pixel value within our window. And what we do is we take the brightness at this pixel value, and we take the brightness at the pixel value plus some direction, so some distance along the gradient of the image. Okay, so we get the gradient of the image and we decide to travel a certain distance along that and see how things go. Now just to understand that, let's imagine that I have an image, this is brightness levels here, that look like as follows. So I have a pixel there, the next pixel is here, and the next pixel is down there. Okay, so and I'll just give these some numbers just to get an idea. So let's imagine that this is 100, this has gone down to 98, and then this is down at something like 90 or something like that. Okay, so at my current pixel, this would be my gradient. Okay, so that's my gradient, that's the direction I'm going. And what I might decide to do is, because of my window, I might decide to go several pixels away. So what this tells me to do is move, let's say, 2 pixels in the direction of the gradient, so in that direction, and then find out what value you get. Now, because the gradient is that shallow, and then we calculate, we're actually getting quite a different number than we might have expected, because we were traveling along the gradient, we traveled a good bit further than that gradient told us, because the gradient only tells us the very local pixel. We travel a certain distance along it and we calculate our number. Okay, and what we do is we subtract that number from our original number, and that tells us how similar they are. We multiply that by whatever weighting is in our window, and we sum all of those up to get an overall idea of the result. So we do that in all directions all around it. Okay, so and so we decide that basically on the direction of the gradient in each case, and how far we want to displace along that. So we sum over each of the pixels in the patch of interest, xi. So wx is a spatially varying weighting function. For example, the weight may be high in the center. So as I say, if it's a Gaussian, it might be high in the center and low on the edges, or it might be just a simple box. That's for us to decide. So this is how we might go around, how we find how much we look like the pixels around us, and we decide how big we want that window to be and how much we're going to look around us, as regards how far we're going to go. So if we look at this section here, that's the kind of midsection that I just drew around. What we're doing is we're comparing via subtraction the same image at the current pixel and the pixel a certain distance along our gradient. So this will give us a single value for a single position, and what we've got to do is we've got to add up a load of those positions to get an overall sense of what the correlation is between them. Okay. So for this reason, we can assume that it's an expensive operation. Okay. So it's not something that we'll do very happily. Okay. So the problem with that is that this idea, the maths of this idea would work very well, but the actual running of it, particularly back in the 1980s when they first came up with it, was going to take quite a lot of computation. Now, we can do it much better now, but the thing is that they came up with all these fast ways of getting an approximation of it back in the 1980s. We're now left with a situation where we're dealing with embedded systems, and we're always short of energy and we're always short of computational budget. So why would we not use these good mechanisms that they came up with? Okay, so this led to a lot of research to find ways to calculate good approximations of the autocorrelation surface. So Lucas and Kanade in 1981 and Shi and Tomasi in 1984 used the first parts of a Taylor series expansion of the image function. Now, how many of you have come across Taylor series, first of all? So Y or an N for Taylor series? Okay, now I suspect all of you have come across at some point. If you've gotten to this far in engineering degrees, you probably have come across it, but you've maybe forgotten it. If a Taylor series, if we were to take the full length of a Taylor series, would be very long, and in fact you can take infinite lengths, and it requires taking a derivative and then a second derivative and a third derivative and so on. And you can build it up in that manner. What we can do is we can have a thing called a linear approximation, which is basically the straight line version of it, and of just the first two parts of the Taylor expansion leads to what's called a linear approximation. How many of you have come across that term, linear approximation? Yeah, so what we're doing is we're approximating a complex function with straight lines. So let's say, for example, I've got some function here like that, and what I do is I'm at this point, and what I do is I figure, well, I'm at that point, my gradient at this point, the tangent to the curve is in this direction. If I travel only a small distance, if I travel only a small distance along this, I'm pretty close to where I would have been on the function. If I travel a long distance along this, we now have a bit of a gap appearing between it and the function. So linear approximations can be very good. If you're not familiar with the idea, I do suggest that you go and watch a video on it. And once again, this here, if you click on that, that will bring you to a YouTube video of an MIT lecture on linear approximation as part of calculus, where he goes through that in quite a bit of detail, and it's an excellent lecture. So do go and look at that if you're not familiar with linear approximation, so that you know what we're talking about here. So the idea that they had was, going back to my drawing here, rather than us traveling the full length of this, what we do is we say, well, our gradient is in this direction. Let's assume that it continues at that level, and let's just take that number there. Rather than actually calculating the real number here, which of course we're going to have some error, but if we assume that we just travel a small distance in that gradient, that would tell us the end number, and we'd probably be pretty close. Okay, so that's the idea. It's an approximation. It's not necessarily going to give us the correct thing if we have a very sudden change, but it might get us close. And the important point is that it's much more computationally efficient to do that. Okay, so what they basically said was, what we're going to do is we're going to replace this with its linear approximation, which is this, which is basically just take the gradient of the image at the current position, which is what I did back here. Take the gradient of the in its current position, and multiply that by whatever distance we want to travel along that gradient, and that will do us. And just add that to our current value, okay, which is kind of what I was showing here as well. Okay, so this is how they did it. They said, well, okay, you take your current image value, and what we'll do is we'll replace the other part of the formula. So just to remind you, this was the formula here. So we're going to replace that with this one down here and put it into our function, which is what we have here. So we've now got this here. Now, importantly, in our function, what you can see is that we've got the value of our image at the current pixel, and we've got the subtraction of that there. So those two cancel out with each other, and we're actually just left with this section in the middle, which is take the gradient at the current position, move a certain distance along it, and tell me what value that is. Okay, so we're really just using the gradients now rather than actually going and taking any measurements. We've got a squared component here, so we better square this out. Okay, so when we square out this section here, what we end up with, I don't know whether you did this in linear algebra or not, but if you ever squared these things that where you've got one gradient multiplied, or you've got one vector multiplied by another, how do you square those? Okay, so what you do is you take the two parts individually, reverse them, put them in the opposite order, and take the transpose in each case. Okay. So Niall is asking there, I presume the shorter the distance you take, the more accurate result. That's definitely the case. I mean, if you take here, if we go over a short distance, we should be damn close to where we are. But the further we go, the less sure we will be about our thing. That's absolutely the case, yeah. Okay. So just be aware that if you ever have to square... there's no specific rules around it. This is a matter of, to a certain extent, trial and error. Because the thing is that if you've got a function that changes very, very quickly, you're going to have more error. The problem is you don't know what it looks like. So the image could throw up anything for you, and you have to make a decision. So this is about the robustness of testing images. In what percentage of images does this work? Under certain circumstances, how well does this work? So, for example, if you're going to be looking for particular things in automotive images, and you're going to be moving at certain speeds, you know, exactly, Niall. Yeah. So in other words, you have to decide how far you're going to go in order to try and get an idea of how far your movement is expected to be. So unfortunately, no hard and fast rules, and that's something you're going to have to get more and more used to at this level. Is that we would have to do quite rigorous testing in order to be that bit more sure of ourselves. So when we square that out, what we end up with is a section in the middle here, which looks like that. Okay, now these are all very complicated looking, but in effect what we're doing is we're getting the gradient of the image with respect to the current pixel. Now the gradient of the image is going to be in the x direction and the y direction, which is why it's shown here as a vector, because that is actually two pieces of information, x direction and y direction. And we've got a transpose here, which means we're going to have two vectors against each other. Because that's going to be a 2 by 1 and a 1 by 2, what will effectively happen with this is that we end up with a matrix here out of this. Okay, and that's our matrix there. It's called A, and we have this on either side here, this and this. Now we've just named it A for the moment in order to simplify life on ourselves, and later on we'll go and deal with it. But the important point of doing something like this is that what we can now see is that there's some sort of a relationship between it and the what we'll call the velocity vector, in other words, where we're headed. Okay? And as you can see, that's multiplied on both sides, and that is the way you would do it if you were trying to get the square of this thing. Now what that basically means is that A here, what we say is it's quadratic with regard to these things. Okay? Now just to remind you, quadratics look kind of like that, kind of a bowl shape. But these are vectors in 2 dimensions, x and y. So what we've effectively got is we've got an actual 2-dimensional bowl here. Okay? And this is, you can almost think of this as like a, if we have a load of pixel values and we're they're at different brightness levels, you have a bowl and how well it's going to fit into those different brightness levels as to how much it's going to change. Okay? So here's our bowl here, and you can see this is our gradient vector there. So what happens is that when we multiply those by each other, what we do is we get the gradient in the x direction and square it, the gradient of the x by the gradient of the y, gradient of the x by the gradient of the y in that direction as well, and then the gradient of in the direction of y squared. Okay, so we've just used the convention of calling that calling the gradients ix and iy. Now importantly, these are not, that's not the second derivative or anything like that. It's the first derivative and then you square it. Okay? And what we can do is we can multiply that by our window again. And the reason that we can multiply that directly by the window up here without the u's is that the window is with respect to x and these are with respect to x, whereas this stuff is not. It doesn't really matter what it's to do with. Okay? Now, I know I'm throwing a lot at you here. This is quite a complex subject, so it is maybe something that you'll have to go back and look at separately. But this is our 2-dimensional kind of quadratic shape here, or quadratic bowl that we get from that. Now, the thing is that, and this is our our velocity vector multiplied by it on either side, which is what gives us this quadratic. Now, if you remember from, and you download this right the way back into secondary school, you used to get these shapes, these quadratic shapes, and what would you be asked to do? You'd be asked to find the roots of them. You'd be asked to find where they cross, let's say where they cross 0. But you could be also asked to say, well, if we set it equal to 5, where does it cross the axis at 5, for example, or something like that? Okay, and they would be known then as the roots of the equation if it's that. In the 2-dimensional direction, that actually maps out a full, it's not a circle because it could be, the bowl could be differently shaped depending on in the x and the y direction. So we actually map out an ellipse in each of these cases. I'll actually leave that there. Okay, so we map out an ellipse. And what that effectively means is that we can do this A vector here, or this A matrix here, which remember is just the gradients of the thing. What we can do is we can do an eigenvector and eigenvalue analysis of that. Now, do you done eigenvectors and eigenvalues, I think, in linear algebra? Yep. Have you got a sense of what eigenvectors and eigenvalues are? Have you got an intuitive sense of them? Or are they just some abstract idea to you? A simple y or n will do on that. I won't ask you to explain it or that. Okay, so you do have some sense of it. Okay, so that's good. So the thing is here that, now as it happens, and you can read this in Szeliski's book, he has a full few pages on it, where he does an analysis of that ellipse and he looks at the eigenvalues of it. The thing is that the analysis that he does is actually on the inverse of A rather than on A itself. But it turns out that that's fine because if we know the eigenvalues of A, we can find out the eigenvalues of A inverse. And if we know the eigenvalues of A inverse, we can find out the eigenvalues of A. Okay, let's just see. I'm just going to test you on that. Let's imagine my two eigenvalues are A1 and A2. And this is the eigenvalues of A, for example. What would the eigenvalues of A inverse be? Do you know what they would be straight off? No need for numbers or otherwise. No, they're not. They're not. Definitely not the same. So the eigenvalues for A and A inverse will not be the same. I can't see anybody. Oh, well, Maurice is typing. We'll give him a minute and see if he gets it. You don't swap them either. No, it'll be basically they will be 1 over and 1 over. Okay, it's the inverse of them. Okay, so if you have an intuitive sense, I think with regards to eigenvalues and eigenvectors, have another think about them in terms of getting the intuitive idea of them. And what I might do at some stage, if you haven't got that, is I might just do a quick explanation to try and give you a sense of it. For the moment, though, the important point is that because these are the eigenvalues of the gradient, they are concerned with what is the major change, what is the biggest gradient, and what is the smallest gradient that we're dealing with within a local region. Okay. Now, the gradient in the x and the gradient in the y will not necessarily tell you that, because you don't know that the gradient direction is perfectly in the x or in the y. So instead, we have these vectors that are in a different axes, the eigenvectors. They're going in the direction of the maximum one and the minimum one. Now, if what the guys basically thought was, if the gradient is big in both directions, okay, it suggests that the change in values will be big in both directions and in all directions, and therefore that patch will not look like its neighboring patches. Okay, so you can see we've taken quite a jump away from the original idea of just checking again against its neighboring patches. Now it's saying, look, if there's a fairly major change in the gradient in all directions, then it's highly likely that the patches will not look the same as each other, and therefore this will make a good solution for a patch. Okay, so let's take some stock in what we have here. We wanted to do autocorrelation, and if we found that a patch was very different from the patch around it, then we considered this a good candidate. But autocorrelation is very intensive in terms of calculation, so we decided to approximate it by using a linear approximation of the image, which required us to get the gradients. If the gradient was high in all directions, then the image was changing quickly there at that point, and this seems a good substitute for determining if the candidate patch would be different from its surroundings. Okay, so this is the approximation they came up with. Now, the problem is that the gradient must be high in all directions. It can't be just high in one direction. If you remember the situation where we had an edge, sorry, I'll draw that as a... Remember the situation where we had an edge, okay? The gradient in this direction is almost nothing. There's no change. But if I go off the edge here, off this, now there is a big gradient. So it's big in one direction, but not in the other. And what we wanted was something like a corner here, something like that. And now we would have a situation whereby if we moved from there in some direction here, that we would see quite a difference in all directions that would occur. Okay, so instead, what we should do is find the principal axis of the gradient by finding its eigenvalues and eigenvectors. Eigenvectors aren't particularly of interest to us, really just the eigenvalues. But actually, so actually the eigenvalues are all we really need to calculate. We're not too concerned about what direction they're in. But what if only one is large and the other is small? Is that good enough? Is that better than or worse than if the two of them are medium in size? Okay, and different people had various different methods of doing this. So these guys, Shi and Tomasi in 1994, what they said was, look, it's all about the smallest eigenvalue. The smallest eigenvalue is going to tell you the smallest change in gradient. As long as it's above a certain level, we can assume the bigger one is even bigger than that, so that'll do us fine. And we'll just check the smallest eigenvalue, and we'll set some threshold. We'll decide, and that decides for you how many features you're going to find in an image or how few you're going to find, by just deciding I'm just going to look at one of the eigenvalues. What that means is you're going to have to calculate the eigenvalues. Okay. Now, I assume you've calculated eigenvalues before on paper. Yeah. So it's for a 2 by 2 matrix, it's not that bad, but it's nowhere near as fast as some of the other things you can do in a matrix. So what Harris and Stevens suggested was, instead of that, what we'll do is we'll get an idea of the two eigenvalues by getting the determinant of a 2 by 2 matrix and getting the trace of a 2 by 2 matrix. Now they also squared it and they multiplied it by a value to get some balance between these two, and the chance they come up with a balancing of 0.06, which you can assume there straight away they were doing a bit of tweaking there to find the right one. What's the trace? The trace, if we have a 2 by 2 matrix, A, B, C, D, the trace is A plus B, or say A plus D. Okay, so that's the trace. It's just the ones down the diagonal there. Okay. What's the determinant of this one, of a 2 by 2? How do I get the determinant of a 2 by 2 matrix? Yeah, which again is going to be very, very fast to do. Okay, just multiply some numbers, subtract, you're done. Okay, so that's pretty quick too. Now the point is here that the determinant is equal to these two guys here, and the trace is equal to the two of those, the two eigenvalues added together. So we don't need to calculate the eigenvalues at all. We just need to do the trace and the determinant, which are very quick, and calculate this. And actually that turns out to be quicker than just checking the smallest eigenvalue. Okay. Obviously the idea of checking the smallest eigenvalue, you have to calculate both eigenvalues in order to do it. Okay. Niall, yeah, okay, yeah, that's great. Okay, so so that's easier for that reason. And it's also rotationally invariant. It doesn't matter what direction that it's going in. Okay. Triggs then came along later and suggested this other type of one, which was that we take a little bit of the minimum one, but we take all of the minimum one, but we also take a small percentage of the maximum one, because that may have some effect on it. Rather than just taking the minimum one, the maximum one might tell us a lot. And I think the idea here was to do with the fact that if the minimum one was big enough but the maximum one was much, much bigger, it mightn't be that easy to tell it apart. It might be more like just a very, very significant edge. And again, you can assume that there was a lot of trial and error going on here, as well as the other idea, and they were played around with a lot of images. And you can also see that, like, this was 1988, this was 1994, and they had a bit more computational power, and this one, Triggs, was in 2004, so there's quite big gaps between these. And what more than likely happened is that they found that some of these were pretty good, but actually there was an awful lot of edge cases where it didn't work in certain applications, so they suggested other ones and got their idea published. And again, but again here you've got to calculate your y min and your lambda min and your lambda max. So presumably they're saying, well, this is a bit more robust, but not as computationally efficient. Okay, so and you've got to make those decisions there, and you as being a master of this area, when you're finished this course and you've done well in it, hopefully, you need to be aware of these different types of ways of doing things and be aware of what the consequences of those are. Some will be more robust, some will be more computationally efficient. If you get a little bit of both, that's great, but you've got to make that decision. And in certain cases, it can be more important to be computationally efficient than to be robust. In other words, in many real-time systems, a late answer is a wrong answer, and that is important to be aware of. Okay. Now, this is the author of the textbook, one of the textbooks that I've suggested to you, Szeliski, and he has a suggestion, which is you get the determinant divided by the trace, which is a thing called a harmonic mean, and basically that's that the two multiplied and then the two added together. Once again, this is going to be computationally efficient because we can calculate the determinant and the trace very efficiently without having to calculate the eigenvalues. Now, this is also from you'll see this in Szeliski's book, and it's from this paper that's mentioned here. He draws some contours. I don't find these contours particularly helpful, but it is interesting to see that they were laid out in this way. And basically what he's saying is that the Shi and Tomasi method, where we only look at the smallest eigenvalue, basically means that if our smallest eigenvalue is 1, it doesn't matter what our other eigenvalue is. It could be anything up the way here. Okay, so we can see that in both cases. Some of the other ones operated maybe a little bit better in the situation where the two were low values. But the question really comes about of what is better. Is it better to have, obviously the great thing is if they're both very large, but if we have small ones, what's the case? So we have this section usually here, which is down in this area here. That's not a good situation. We have a small value of both eigenvalues. That's not good. If we've one big eigenvalue and one small eigenvalue, which is either in this section here or this section here, that's kind of okay. That's pretty okay usually, as long as the second eigenvalue is not very small. And obviously if we're in this section here, it means both our eigenvalues are big, and that's great. And that means that we've got something that works well as a correlation, as a patch or a feature that we're going to do. Okay. So here's the full layout of a basic interest point detector as to how we would do it. So compute the derivatives in the x and the y directions of the image, and we call these ix and iy by convolving the original image with derivatives of Gaussians. And you can see the section 3.2.3 in Szeliski's textbook for doing that. So that's the first thing we do. We then compute the three images corresponding to the outer products of these gradients. That is back here. Sorry, it's a good bit back. It's further. That's these three. So you need to get ix squared, iy squared, and ix iy. They're the same. Both of those are the same. So therefore, once you calculate it once, you don't need to calculate it a second time. But that's effectively three different images that your image worths of information that you're calculating there. So just for anyone watching the recording, we'll continue on this slide, because I think we probably got as far as this slide before we had our break there. So we compute the derivatives in the x and the y directions of the image. They're called ix and iy. So ix and iy by convolving the original image with the derivatives of the Gaussians. Compute the three images corresponding to the outer product. So that's, you get I squared. You get ix squared, iy squared. So that's ix squared, iy squared, and you get ix iy. And of course ix iy turns up twice in that A matrix, so that's fine. So you just compute those three. Convolve each of these images with the larger Gaussian. That's the w in the equation. And so that's the window. You decide what size of a window you're going to do it in. Compute the scalar interest measure, which is, you use one of those methods that we showed there of the eigenvalues. Decide which one you're going to use, and decide what your threshold is going to be. Above what does your eigenvalues or your combinations of them have to be before you decide that they're good enough. Find the local maxima above a certain threshold and report them as detected feature point locations. And finally, you may find that there are many points all clustered near each other. So you can look at the adaptive non-maximal suppression algorithm in Brown, Szeliski, and Binder. They only include features that are local maxima and with a response that is significantly higher than 10%. So this is another further algorithm on top. Can I just check with you guys? We're finished there now. Did Louise move her class to Tuesday night or that? She was talking about possibly doing that. She hasn't done that for tonight anyway, I assume. No, that's fine. If you have 5, you can head now if you want, but if you have 5 minutes, I'll try and give you that kind of intuitive explanation of eigenvalues if you want to hang about. Do you want me to do that? Okay, so we'll give that a go, and we'll just include that on the end of the recording. Okay, so what I'll do is I'll use my mobile phone here, and as an example. Now, matrices can either describe a thing, such as a thing here, okay, or they can describe a transformation of a thing. Okay, so how it changes that thing, so maybe how it moves it or something like that. Okay, now it doesn't matter what orientation I put my phone in. the eigenvectors of this would be the same. So you can think it, now I'm being very loose with my description here, but it'll give you at least an intuitive idea. So you can consider the eigenvectors of this object here to be that one there, which goes along there. You consider it that long one there, and then we've got a very thin one here that goes up in that direction that would describe that. Okay? So they would be the eigenvectors, and the eigenvalues then would be the length of that, the length of that, the length of that. Okay, so we've got one small eigenvalue here, one large or one medium, let's say, eigenvalue here, and one long eigenvalue here. Okay. Now imagine I transform this. I can move this about in all sorts of directions, but its eigenvalues don't change. So whatever matrix I'm doing to transform this or to move it about, they all have eigenvalues in every direction of 1, because it doesn't change. It hasn't, by moving this about, I haven't changed the eigenvalues of the object that I'm transforming. Okay? Now imagine, for example, that I could do some transformation on this, and what I did was I made it twice as fat as it is. Okay? What would happen is, in the transformation matrix, is that eigenvalue, the transformation along that direction would be 1, because I don't change the length of it. I don't change that length there, so that eigenvalue would be 1, but I've made it twice as fat, so the transformation there would be an eigenvalue of 2 along that vector. So it would make it twice as fat. If I want to transform it back, I'm going from twice as wide to only half as wide. So again, eigenvalue there would be 1, because I haven't changed it at all. I haven't changed this one at all. But this middle one here, I've gone from this wide down to this, down to half the amount. So you can see why the transformation to make it fatter would be an eigenvalue of 2, but the transformation in the other direction would be 1 over 2, because I'm making it half that. So the idea of the inverse of some transformation matrix is that I'm trying to move it back to where it was, and I would be changing those principal axes there. Okay, so that's the idea, that the inverse of that matrix, all we need to do is, if I can calculate the matrix eigenvalues in one direction, the inverse of it are trivial for me to do, because I just get the 1 over that to send them back in the other direction. So that's the idea of that. Does that give you a bit of a better idea of maybe a physical way in which the eigenvalues are used? Yeah. Okay, so that's good. And we'll be coming across this quite a lot, because we'll be doing transformations of things, so we'll be rotating things and so on. And what you're going to find is that rotation matrices have eigenvalues of all 1, because they rotate things, but they don't change them physically in size. So they don't change their volume, or they don't change their area, and for that reason they would be called orthogonal matrices or orthonormal matrices. Did you come across those in linear algebra? We have all eigenvalues of plus 1. You mightn't have done, no, I'm not sure. Okay, well, okay, that's fine. When it comes to these things, obviously I won't be going through them in detail, but I'll be able to give you some YouTube videos and so on that you can go and watch if you want to get a little bit more detail on them. So guys, we'll leave it at that. Sorry about my few little crashes tonight. I think what we'll do the next night is we'll split it into 4 half hours, and I think that way we're less likely to have these issues. The reason that I'm having these crashes is purely because I'm trying to show the webcam and trying to record off the iPad and trying to do several things at the one time, and I'm just pushing the resources a bit too far. Okay, but hopefully you're okay with that. So we'll finish the recording there.